right. Hi, I'm Isabella,
I'm David.
and this is Intro to Rust.
So what we're going to do is just give a really lightweight introduction to the language, walk you through a few of the language features and some of the ideas behind the motivations why you might want to consider using it in your next project. And it's a relatively new programming language, but it's gaining a lot of traction. It's in use at large companies like Facebook, Google, Microsoft,
Mozilla, Amazon.
Yeah. Most major companies are using it to some extent, and it's likely to grow in the future. So the first question is, the first thing that we should say is like everything that we share is just going to be adapted in some way from the official Bible, which is the Rust book. So if you're interested in any of this, you should, after this, go to this URL, read the Rust book. It's really, really great. We definitely found that it was the most informative text on programming we've ever read.
Yeah, on programming in general.
Yeah.
So,
So the first question is, there's a lot of programming languages out there. Why do we need another one? And what it really comes down to is that the creators wanted this. They wanted to be able to write code that runs as fast as it would if it were written in C or C++, but make it accessible to a much wider audience, the kind of people who are familiar with JavaScript or Python, and give you the convenience and joy of use that attracts people to languages like JavaScript and Python. So here's like a business 101 graph. On one axis there's performance, on the other one there's ease of use. You can see JavaScript and Python are quite easy to use, but not so great on performance. Then there's C++, which is really, really fast, but not so easy to use. And the goal with Rust is to occupy that top right corner. So first, I'll just go through a really quick getting started. So the first thing you want to do, if you want to get started, get back to the browser, is go to rustup.rs. You can do this now, you can do it on your own time, and there's a one-liner. You copy it, you paste it into your terminal, and just like that, you have Rust installed. They make it really, really easy to get started. So then what you can do is, I've already run this on my computer, so what I can do is, I'm in my home folder right now, and I can create a new project using Cargo, which is Rust Package Manager. It's kind of like the equivalent to NPM, so you know the use of NPM init to create a new project. With Rust, you would say Cargo new. I'll make a new project called Hello World, and what it does is it creates a folder. I'll cd into it, and it creates a single main file and a cargo.toml. The cargo.toml is a manifest. It's just like package.json in Node.js. It's where you declare your dependencies and the name of your package and set up all sorts of stuff to publish it. So I'll open this up in VS Code and show you this. Just a moment. I'm going to open that folder up. So in that folder, here's the manifest file. You can see, let me just hide this from, sorry. You can see how I've created a package, and its name is hello, and it has no dependencies right now. And then if I go to the main RS file, you can see there's a main function that says println hello world. So I'll jump back to my command line, and I'll say cargo run, and that will build and run the program. So it compiled it, and then it just printed out hello world. And there's this special folder called target, and that contains all of the built files. So if I look under target debug, then hello, you can see that's the executable file. So if I were to run, for example, target debug hello, if I were to run that file directly, it would get the same thing. And when it's time to release your software in the real world, you probably want to say cargo build, and then pass the release flag. That builds it with all of the optimizations you need to run it like on a real server.
So the compilation is longer, takes more time, but the resulting binary runs faster.
Cool. And regarding dependencies, so in order to get that NPM style experience, you can use dependencies from the registry. It's not called NPM, it's called crates.io. You can search for anything, like let's say you want to generate random numbers. I can search for the word rand, I find this crate, and then I can add it to my manifest. I'll jump back here, I'll go to here, and under dependencies, I can say rand equals 1.0 or whatever version it is, and now I'll be able to use that crate from my code. You don't even have to run npm install or anything.
You'll run cargo run and it'll install.
All right. So if you're using Rust, you'll be on crates.io a lot looking for dependencies. You'll also go to docs.rs, which is where you can, I'll look up that rand crate, and you can see the documentation for it. This is one thing that makes all of the Rust packages really accessible, is that there's a standard form of documentation. Every Rust crate has the documentation on the same website. You can look any of them up. You can click on the structs, the functions. Everything is very nicely documented. It's really convenient. If you want to look into the standard library also, you can go to std.rs. Here there's full documentation for the standard library. The standard library has things like accessing the network, accessing the file system, etc. All right, let me jump back to the slides. All right, do you want to take this section?
So here's an example program. We create a variable x, we assign the value 5 to it, and then we assign the value 6 to x. And if we try to run this, the compiler will complain at us. Rust compiler is very friendly. The error messages are very interpretable, and this was very intentional by the creators of Rust. So here it says the first assignment to x. You can't reassign to it. You need to make the variables mutable.
What you often find with programming Rust is that you're kind of having a conversation with the compiler. You try to write something. The compiler comes back and tells you, oh, that you made a mistake in such and such way. It often recommends corrections. But you'll often find that if your code compiles, it will run successfully. And we'll go through some of the features that show how that happens.
Mm-hmm. So to fix our code, we'll just declare that the variable x is mutable, and then
you can see it says let mute.
Let mute x.
So Rust is a compiled language versus here we're going to pick on JavaScript, which is an interpreted language. And we'll just talk a little bit about some of the differences between these two languages for this really, really simple function. So in JavaScript, when the function add, it takes two arguments, x and y, and it returns the sum of them, right? What does the JavaScript interpreter have to do? First of all, it has to actually interpret all of these. So it reads like character by character, like F, U, N, C, and then figures out the whole structure of your function, right? But then, when you say x plus y, what it needs to do is ask, is x actually a number? It might be an object or a string. So it checks that and throws an error if it isn't. Same thing for y. And then for each of them, it has to go and retrieve the actual number values, and then finally add them together. What the Rust function can do is, because it knows that x and y are both F64s, those are 64-bit floating point numbers, what it can do is it can just immediately add the two values together. And wherever you're calling the add function, it can just inline the assembly code. So it's almost as if you didn't even write a function. There's no overhead. And so the result is, in the case of this function, wherever you're using it, it's just one assembly instruction, and add.
So compiled languages run faster.
And with strong types. Do you want to go through this example?
Sure. So in the first example, we're creating a string in Rust, and then we are mutating that string, pushing a value world to it, and then we assign to hello world the string hello. And we do the same example in JavaScript. And then you want to explain?
Sure. So in JavaScript here, what the JavaScript interpreter will be forced to do is to copy the string hello before creating the string hello world when you add the two strings together. And the reason is because JavaScript has a garbage collector, and it won't know ahead of time that the variable hello is not being referred to someplace else. I mean, we can kind of see it just looking at the 2 lines of code, right? But the JavaScript interpreter doesn't know that. Whereas in the Rust example, because the variable is mutated directly, you don't have to copy the string. So we're just kind of giving another example.
There's 2 allocations in the JavaScript example and only 1 in the Rust.
So you often, when you're writing code, you don't want to have just strings and numbers. You want to combine things into meaningful structs. This might be called interfaces if you use TypeScript, or in many languages you use classes. So here we're defining a user struct. It's this person has a username, email, etc. And then I can create one. I can create one just by naming the type, using curly braces, and then key colon value. And then, structs are, they're what's called sum types. They're what's called product types, where the number of possibilities is the product of the number of possibilities for each of the fields in the struct. What Rust also has is enums, which are called sum types, where the number of possibilities is the sum, not the product, of the number of possibilities for each of the fields. So here's an example of an enum. This is an enum like in other languages, where a coin could be one of a penny, nickel, dime, quarter, etc. But there are also enums that take in actual values. So this is a very important enum in Rust called option, where it's either none or some with some types. You could have like an option of a string or an option of a number. And then what Rust has is what's called a match statement, which allows you to pattern match on all of the possibilities for that option. So in this case, in the code you see here, the variable O is an option string. And so you might have a string or you might not. And with the match statement, what we're doing here is we're accessing the string if it's some, meaning that there is a string there, or we're printing out nothing you see here if there is none. And this solves a big pain point in C and C++, which is null pointer dereference. It's the cause of like just about every single crash you ever have on your computer. What's really cool about the code snippet, even though it looks kind of simple, is that you can't access the string until you've already checked that it's not null. Oftentimes, programmers forget to check whether things are null. They don't know whether they have to check whether things are null, and things crash. And it also causes a lot of security vulnerabilities.
And some people return like -1 or something. You don't have to do that in Rust. You get explicit none or some of the value.
This kind of goes back to what we were saying about how the programmer is protected from him or herself, because the language makes sure that you cannot access things that are invalid. And the same thing goes for functions that might return error. So the result enum similarly has two variants, either OK or error, and you can only access the associated values for OK and error if you match on them first. So in this example, we attempt to read from a file, and that might either succeed or it might fail. So if it succeeds, then you can access the text of the file. But if it errors, then you can access the error and print out the error. Does anyone have any questions about this? Cool.
Iterators. So iterators in Rust are really cool. Just like you have iterators in JavaScript, you also have them in Rust. These are the same code examples, just one is in Rust and one is in JavaScript.
And what's really cool here is if you look at the JavaScript example, what the JavaScript interpreter is forced to do is first it has to map the entire array, it has to copy the array, and then add one to each of the items. And then finally it can add them all together. That's because the JavaScript interpreter doesn't have access to the full code until it's already being executed.
So it means there's an extra allocation there?
Right, whereas the Rust compiler, what it's able to do is ahead of time look at the full extent of what you're doing and produce really optimal code. So in this case, what the code the compiler would produce, even though it looks like very high level code, it would produce the best possible code as if you had written it in assembly, which would be just adding up all the items and then adding the length of the array.
So that's like another point about Rust. Like there's a lot of combinators that makes it feel like you're writing very high level code, but the Rust compiler is really smart and it figures out how to reduce that code to something that you wouldn't really be able to handwrite better.
Exactly. And that's playing towards the goal of being as fast as C and C++, but as easy to use as JavaScript or Python. So last section is on borrow checking. This is another example of how the compiler really has your back to make sure that you are writing code correctly.
And this might be a place where you feel like you're wrestling with the compiler.
Yeah.
I think borrow checking is one of the things that is the most frustrating when you're going back and forth with the compiler.
But what you often find is that the compiler is smarter than you. It knows mistakes that you made before you even realize them.
So here's an example where we create a string, and then we want to push to that string. We want to mutate that string. And the change function takes in a reference to a string. And let's see what the compiler tells us about this code. It says that ampersand string is not mutable. So we can't actually call this function push string, which mutates some string, because some string is not declared as mutable. So the compiler is telling us that we have to explicitly specify that the change function takes in a mutable reference to that string so that we can actually mutate it.
So this often comes up in code where someone writes a function which is like compute something based on this string, right? But then some other programmer comes along and they say, oh, I'm just going to start changing the string.
Yeah.
Somewhere deep, it could be a massive function, right? This happens all the time in huge code bases where people start changing things where they were only supposed to read it. What the REST compiler does is it forces you to declare up front whether you're going to change it or whether you're just reading
On the
it.
function signature.
Okay.
So if you notice here, the two changes that were made were that you have to declare that S is an ampersand mute at the call site and at the function definition site. So that's why you see change is an ampersand mute S now, and the function signature also takes in an ampersand mute string. Also, another problem that you might face if you're writing
If you're writing C, mostly, yeah.
is that you can return a dangling reference. So inside this function dangle, we create a string, and then we return a reference to that string.
And that's not really a big deal in the garbage collected language because the reference will, the garbage collector will ensure that the object being pointed to survives for as long as the reference survives. But because Rust isn't garbage collected.
In Rust, S will no longer exist at the end of the function scope, so you'll be returning a reference to something that no longer exists. And the compiler will complain. It'll say something about lifetimes. It'll say the lifetime is not long enough, which just means that this value is not living for as long as you want it to live, so you can't actually refer to it.
This error message says it wants to live with a static lifetime, which means living forever. Because when you return a reference from a function, you're basically saying that this reference must live forever. So what we've done is we've just tried to give you a really small little taste of some of the ideas behind Rust, and hopefully you will feel inspired to go read about it yourself and learn more. It's really cool. We strongly recommend it.
And one motivating thing, we deleted the slide. It was 70% of bugs in Chrome.
Security vulnerabilities.
Security vulnerabilities are because of memory issues that Rust would have
That are not possible.
not possible.
Exactly right. Because of all the protections provided by the compiler.
So it's a big motivator for a lot of these companies to start writing projects in Rust. It's a lot safer for security reasons. And it's really popular.
All right, we have there are a couple questions.
Yep.
Great.
One is, do you think Rust reflective features are superior to those of C++?
Which features?
Reflective features?
So Rust does not have any reflection capabilities. Everything that you write at compile time melts away. There's no runtime type inspection.
All right. And then second question is, do you think C++ is significantly more powerful than Rust in terms of language constructs? Parentheses, the ability to emulate the features of other languages, even if ugly.
I don't think I have a great answer to that. I would say that Rust actually currently has a lot of those features that are forthcoming in C++. Like the upcoming concepts feature has been implemented in Rust since the beginning. It's called traits. So I don't know. It's too broad of a question to answer directly. It's a balance.
All right. And then last question is, how do you use Tangram with Amazon EC2/Lambda? Yeah.
Yeah. So if you turn on an EC2 machine, it's probably Ubuntu. You can just apt install Tangram following the instructions on our website.
That's all the questions I have.
Cool.
Another thing to note about Rust and C++ is Rust is very accessible. I think C++ is not very accessible. And the Rust book it reads, like you can read it at night, like you would read any other book, and it's like a refreshing programming book. It reads like a novel.
There's a very nice on-ramp to high-performance programming from, scripting languages that a lot of programmers use today in Rust, and it's rather difficult to get into C and C++. They're complicated languages, and they also have a long legacy to maintain. And so, there are 10 different programming languages buried in C++.
Yeah, so while Rust is a very low-level systems programming language, it's very beginner-friendly. And they have a very welcoming community. Yep.
There's just one more question that came online that was just asked. Chrome, from Anonymous, Chrome does have a lot of security concerns, but what about Rust prevents these? Can you clarify?
Sure. So according to the Chrome team, and this is actually across many projects, that Microsoft recently reported the same, that 70% of their security vulnerabilities boil down to using a variable after it's already been freed, meaning you're accessing memory after it's been destroyed, or other memory safety issues, like if you take 6033, have any of you taken 6033 yet? You learn about buffer overruns, where you access values in an array outside of its length, meaning you get the length wrong. So anyway, these companies report that about 70% of their security vulnerabilities boil down to those issues, which, if you're using Rust correctly, are theoretically impossible because of all of the safety capabilities that the compiler provides.
Great. I think that's been all the questions we have from our virtual audience. Do we have anything from the live audience?
So Rust is a lot faster than Python, right? But Python is still pretty fast. So how noticeable is the speed up?
It's difficult to provide a precise number because it depends on what you're writing. Code that you write in Python where you care about performance can be quite fast, typically because you're using libraries like NumPy or Pandas that are actually written in C. But if you try to write those same algorithms in Python, if you can write your code in Python, it's going to be horrifically slow. Something you write in Rust might be 100 times faster and use substantially less memory.
So sometimes it feels like you're using Python code, but you're actually communicating to C code through the Python program.
We have another question that just came from online. Do you believe smart pointers are insufficient to help legacy languages at this point? And I'm pretty sure they're mostly talking about like C++.
So smart pointers are definitely a good step forward. However, they have a runtime cost. The whole point behind some of the features we're showing in the Rust compiler is that they only have a compile time cost. So you're able to get the benefits of smart pointers at compile time, not runtime. So the resulting code is faster.
Do you have a question, please?
Yeah, I guess I was just curious that, do you still think that there are flaws in Rust where choosing another language like React or like another language would be more beneficial, or do you think that Rust will eventually overtake more of the space that is used for say web development or something?
Yeah, it's a really complex question. I would say that JavaScript is full of warts as well. Things like, have you ever tried to say null equal false in JavaScript? There's a lot of strange stuff going on in JavaScript that makes it inaccessible to some extent. However,
it's kind of like a societal question.
Yeah. However, Rust, the primary problem with Rust is that even though its goal is to be as easy or as accessible as possible, it's still not the easiest language. It's definitely not the kind of language that I think anyone would recommend as a first language for someone to learn. But many people start programming in JavaScript or Python or other languages.
Python's probably easier than JavaScript. JavaScript has some weird stuff, like prototypical.
Yeah, I know. Python, it almost reads like English. It's definitely, I think this is, for very good reason, 601 and other classes start with Python.
I think we're like almost out of time, but I think we do have time for one more question. There's a question that just came from online. I have heard that Rust has threading guarantees. Do these derive from Rust's memory model?
I believe the answer is yes. That's exactly right. So when you're writing multi-threaded code in Go or C and C++, you can pass pointers between threads and then access memory simultaneously, which is very bad. Bad things will happen. To prevent this, what you do is you use mutexes. But you as the programmer have to remember to use the mutex. What if you forget? Sometimes if you're like only reading memory from multiple threads, then you can just, then you don't need a mutex. But if you're reading and writing, then you need a mutex. What the Rust compiler does is it guarantees that you cannot send references to other threads unless they're wrapped in a mutex or some other protective structure.
And the compiler will say like blah
Yeah.
is not send. or
Yeah,
blah
exactly.
is
The
not-
compiler will tell you exactly what's wrong. You cannot send this value to another thread because you need a mutex.
Cool.
So I think we're at the end of our time. We're at the end of our time, and so we are good to end if you are.
That's good.
All right, thank you so much to Tangram for coming out.
Thank you.